Okay, good day. Today I'm going to be showing you how to design a frame, the beam on a frame, which is this one, and the column. This is going to be symmetrical because the load is only coming from the top part. Okay, this is going to be a beam with a brick wall on top of it. The brick wall will be carrying a truss like this. Normally, you will find out that if you do your calculations and you're in Zimbabwe, for example, you will find out that the height from this point to that point is normally 0.7 meters. So the beam that I'm going to be using is going to be 400 millimeters deep. So it means that the thing that will be left is going to be 0.3 times the thickness of the wall, which is 0.23 times. Okay, this is the length and the width. So I'm going to multiply it with these two. Then the density of the wall is 23 kilonewtons per cubic meter, which is going to give me let's say 1.6. So the brick load is equal to 1.6 kilonewtons per meter. Okay, let me explain how we came to this value. If we have a density, for example, 23 kilonewtons per cubic meter, as you can see, this means that we've got 23 kilonewtons for every cubic meter, right? Then we multiply this with the area here by area with the thickness of the wall, which is 230 millimeters, which is 0.23 meters. Okay, we multiply that with the height of the wall, which is 300, which is 0.3 meters. Okay, this meters and this one will cancel out with these ones. So you'll be left with this value multiplied by this value multiplied by this value, which will be 1.6 kilonewtons per meter. So this is the UDL that we are going to use. Then we are going to have the self weight of the beam itself. So for the beam now, what we do is this: we have the section is going to be 0.4, which is the height, times 0.3 times the density of concrete, which is 24. Okay, this will give me, let's just do it, 0.4 times 0.23 times 24 equals, which will give me 2.2 kilonewtons per meter. The same principle applies. So we've got, for this thing, we've got 1.6 plus. For the brick wall, for the concrete, we've got 2.2, which is going to give me 3.8. So this and this is going to give me 3.8. I'm going to do an assumption for the top part here. Let's say the roof is going to give me a load of, actually, the roof will give you a load that is less than 1 kilo Newton per every square meter. Okay, depending on the orientation, this is going to be an example. So you have to calculate that based on a real life application. This is going to be an example. So for this, I'm going to assume that this UDL, as you can see, we said 3.6 is the brick wall. So I'm going to add to that, let's say 5. So I'm going to add, and it's going to be 8.8 kilonewtons per meter. Okay, this is my assumption. So I've got a column here, I've got a column here. Okay, for this column now, since this section, if we can draw the section like this, we are going to have 400. Then this is going to be 230. Okay, so this one, I'm going to assume it's going to be a square, a 230 by 230 section. Okay, this is important in analysis. The size of the column is of vital importance. Okay, another thing just before we move on, as you can see, if I have a beam like this, a frame like this, and then I apply a load here, it's going to bend in this direction. Okay, what is going to happen if the angle at the support here is constant. Here it was 90 degrees, and here it still remains 90 degrees. It means that this is called a fixed joint. Once it's a fixed joint, then moments are transferred beyond this node. So if it's pinned, what was going to happen if it was going to be pinned? We were going to have something like this. Then the wall would remain like this. This is normally consistent with brick walls. Okay, this means it's pinned. When it turns together like this, it means that this is a fixed joint. So I'm going to assume that this point and this point are fixed. Right, thank you. Let's move on. Now, if we have a frame system like this, and we want to do what is called a moment distribution, we assume that this is going to be 8.8 kilonewtons per meter. Okay, the first thing is we want to calculate I, and I for this section, and I for this section. Okay, so I for this section, I, if you still remember, it's actually IXX. Okay, it's going to be BD cubed divided by 12, which is going to be, for this one, is going to be 0.23 times 0.23 to the power 3 divided by 12, which is going to give me 0.000232. Okay, meters to the power 4. Okay, that is for this section. Right, the second one is going to be BD cubed divided by 12, which is going to give me, instead of using this, I'm going to use the D is the depth of the section. So the depth of the section in this case is going to be 0.4 like this. So it's going to give me a different answer, which is 0.001226667. Okay, cubic meters to the power 4. Okay, so that is my I. Right, the first thing that you do after you've done this, after you've come up with an I, you want to calculate the fixed end moments. So the fixed end moment, this is the first stage in dealing with this moment distribution. It's the method that we're going to use. So when I'm doing my moment distribution, I calculate what is called the fixed end moment. I assume this is my A, my B, my C, and my D. So from A, B, you say FAB is equal to 0, which is, then FBA is equal to 0, because we don't have a load here. Okay, this is the same for FCD, which is also equal to 0, and FDC is also equal to 0. Okay, now FBC is equal to minus omega L squared divided by 12 for the fixed end moments, which is going to be minus 8.8 times 6 squared divided by 12, which is going to equate to, let me just calculate, minus 8.8 times 6 squared divided by 12. Okay, it's going to give me minus 26.4 kilonewtons per meter. Kilonewton meter, sorry. Kilonewton meter, since it's a moment. FCB is going to give me it's going to be omega L squared divided by 12, which is going to be 8.8 times 6 squared divided by 12, which is going to give me 26.4 kilonewton meters, since it's a moment. We'll come back to this in future. It's so important, so I'm just going to place it on the side. Okay, now we have the fixed end moments. What is the next stage? The next stage here is to calculate what we call the K, which is called the stiffness. The stiffness AB, I'm not interested in that. I'm only interested in stiffness going in this direction, that direction, in that direction, and in that direction. So I'm going to calculate K BA. I'm going to calculate K B C. I'm going to calculate K. C, B. I'm going to calculate K, C, D. Okay. So I'll just calculate this. Okay. When I'm calculating my K, the formula for calculating K is 4EI divided by L. The E is actually constant for everything, so I'm not going to be worried with that. But I will be going back to my I's since they are a bit different. Okay, let me do this. This is the first I that we said, and this we said it was for the column, as you can recall here. Here, this is the one for the column. Okay, so I'm going to do this. This is going to be 4 times. I'm just going to ignore the I and write 0, 0, 0, 0, 2, 3, 3, 2 divided by L. L is the length here, which is this one. I said it's 2 meters, if you can recall, divided by 2. This is also in meters, this is also in meters. So it's okay. This is the number that we're going to come up with. Then I'm going to calculate to find out. I'm going to say 4 times 0.000233 divided by 4 equals, it's going to give me 0.00030 here. 2. There must be something wrong. Okay, I made an error here. This is supposed to be a 2. This is supposed to be a 2. Okay, 0.000. This is going to be 4, 6, 6, 4. Okay, let's just leave it like that. Let's go to this one. The formula is the same. So it's going to be 4 times 0, 0. Okay, for this one, it's going to be 0.001226667 divided by the length is 6 meters. Okay, so it's going to give me, let me calculate that one. It's going to be 4 times 0.001226667 divided by 6, which is going to give me 0.00030081778. Okay, now if we do this calculation, it's so similar to this one since it's symmetrical. So here I'm going to get 0.000817778. For this one, I'm going to get 0.0004664. Okay, now after we are done with the stiffness, we want to calculate what is called the distribution factor. So for distribution factor, I'm going to go BA, distribution factor, BC, distribution factor CB, distribution factor CD. Okay, these are important. The formula is the same throughout, so I'm going to write it once here. The formula is going to be K, in this case KBA, over summation of K at B. What do I mean at B? As you can see here, we've got the node B. So at B, all the K's, all the stiffnesses that start with the B are at B. Okay, so in this case, it's going to be this one, which is going to give me 0.0004664 divided by 0.000817778 plus the other one, 0.0004664. Okay, what is it going to be? Let me just check my calculator. Okay, it's going to be 0.0004664 divided by 0.0004664 plus 0.000817778, which is going to give me 0.3. Let me just leave it to 3 significant figures. 363. Okay, this is going to be my distribution factor. If I'm going to add this one in the next distribution factor, it should give me a 1. Okay, let's go. For this one, it's going to be almost the same, but it's going to be K Okay, let me repeat this one so that we'll skip these two. KBC over summation of K at B, which is going to give me 0,000817778 divided by 0,000817778 plus 0,0004664. Okay, if we check, we can just change the first few numbers here, 3 zeros, then we are going to say 81778, enter. Okay, so it's going to give 0,637. Okay, let me add these two. 0,363 plus 0,637 is going to give me a 1. So it means that we got it correct. Okay, this one is going to repeat here. It's going to be 0,637. I said it's symmetrical. Okay, for this one we're going to get 0,363. Okay, now that we are done with the distribution factor, we are moving to my favorite part, which is the moment distribution. When we are saying moment distribution, I first of all draw a line like this. I'm going to leave this for the comments and all that stuff. Okay, the first two are important. This is going to be my distribution factor. This is going to be my fixed end moments. Okay, right. We have an A, we have a B, we have a C, and we have a D. Between these, we have to add lines like this. Okay, once we are done, under B, since we have 2, we have to add 2. We have to split this into 2, right? Now we are done. Okay, what is going to happen? I want you to remember this. Whenever you see something like this, when it comes this in distribution factor terms, it will give you a 0. So the distribution factor for a fixed point is a 0. Then the distribution factor for a pinned one, like this one is equal to 1. It has to sink into your mind because this is very golden. Please remember it. Okay, so in this case applies. Since it applies at A and at D, so at A we are going to get a 0. For this one we're going to get a 0. Okay, then we are going to copy the distribution factors. We're going to use these distribution factors. As you can see, distribution factor BA from B, this one, sorry, I was supposed to do something else. Okay, this one is going to be an AB, this one's going to be BA, this is going to be BC, this is going to be CB, this is going to be CD, this is going to be DC. Okay, this is important. I left it out. Okay, right. These two, they lie under the point B. These two, they lie under the point C. Okay, right. For this distribution factor BA, we are going to use 0,363. For the next one, 0,637. Okay, I'm going to check this one with the computer when I'm done. This one is going to be 0,637, and the last one is going to be 0,363. Okay, now we have the distribution factors. Now we want to move to the fixed end moments, which is the first thing that we calculated, if you can still remember. And the fixed end moments were these ones here. So we say this one is going to be a 0, this one is going to be a 0. As you can see here, this one is going to be a 0 and this one is going to be a 0. For this one, we're going to have minus 26.4. For this one, we're going to 26.4. Okay, when we are done with this, let me just add a few lines here. It's normally done 5 times, only 5 times. The answer will be insignificant for us to continue. The first thing that we do here is we find what is called the first thing that we do is what is called a moment distribution. Then we do what is called a carryover moment, and we keep repeating this up until we have insignificant values. Okay, for you to do what is called a moment distribution, you have to distribute moments upon this at B. Okay, for you to distribute at B, you use these distribution factors. For this to be 0, you have to add up these two. We are going to say minus 26.4 plus 0 equals, you come up with this answer. For it to be a 0, you have to add the same value, which is 26.4. For you to add 26.4, you're going to say 26.4 is actually 26.4 multiplied by the distribution factor, which is this one, which is 0.363 equals. It's going to give me a 9,5832. Okay. The other one, you're going to use the other distribution factor, which is 637, which is going to give me 16.8168. Okay, if you add all these four numbers here, you should come up with a 0. What we are saying, we are actually distributing a moment in such a way that it cancels out the moment that we have to start with. Okay, so this is going to repeat in this nature. Now if you add this one, you're going to come up with 26. So for it to go to 0, you have to add minus 26.4. So this is going to be minus 16.8168. Then this one is going to be minus 9.5832. Then this one is going to be 0. Okay, this is how you distribute the moment. Now what we do, this is going to be a 0 for now. Okay, you are going to carry over this moment to this box. You're going to carry over this moment to this box. This one you're going to carry it over like this. This one you're going to carry it over like this. Okay, for you to carry over the moment, you just multiply it by half. You say half of this moment is going to be transferred to the other joint. So in this case, 9.5832 times 0.5 equals, is going to be 4,7916. Okay, this is almost the same as this one. It's going to be minus 4.7916. Okay, now we are going to the next one, which is this one, 16.8168 times 0.5 equals, which is half, equals, this is going to give me minus 8, it's half of this one. So it's going to be minus 8,4084. This is going to be 8,4084. Okay. Now we have distributed this moment. Now at this point, we want to distribute the moments at this point. So it's going to be moment distribution. At this point, this is going to be a 0. You multiply this with the distribution factor, it's going to give you a 0. Whether it was a minus or a plus, so it is insignificant for me to record it. Now we'll come back to this section. Now after we've done this, we were going to go to the middle span. Okay, now for us to distribute this one, we are going to deal with this one, which is 8.4084 times the distribution factor. Since it's 8 this, so that it cancels out to this one, we're going to multiply it with the distribution factor, which is 0.363 equals, it's going to give me 3,0522. Let me leave it like this. Okay, now the other one is actually 637. Okay, it's going to give me 5,356. Okay, these are the values. They're going to be positive to cancel out this one. In this case, they're going to be negative. So this distribution factor means this is going to be minus 3,56. Then this is going to be minus 3,0522. Okay, now we've distributed these moments. We are going to do a carryover moment like this. This one is going to be carried over like this. That one like that. That one is going to go in that box. Okay, this is called a carryover moment. Now we have to repeat this process until we have numbers that are less than 1, so that our accuracy that are less than 1, as in we are looking for decimals. When we've got decimals, they become insignificant. Okay, so let's continue. This is going to be 3,0522 divided by 2, which is going to be 1,526. Let me leave it like that. Okay, for this one, which is sorry, the comma is misplaced here. 5 I will have to remember at some point. 5,356 times 0.5 equals, which is going to give me 2,6867. So 678. This is going to be minus. This is going to 2,678. This is going to be minus 1,526. Okay, let me just do it one more time. I think it will be reduced to insignificant values. We're going to do a moment distribution like that. Okay, for this one it's going to be a 0. I'm not going to record. Okay, this is going to be a 0 here, 0 there, 0 here, 0 here. Okay, for this one I'm going to redistribute this moment, which is 2,678 times 0.363 equals, which is now, we are now in the range that is less than 1, which is good. So this one is the lesser one. Okay, so if we multiply here, we are going to get 0,972. For this one we are going to get, it's going to be 637, enter. It's going to be 1.706. okay, for this one it's going to be minus 1. Since this one is positive, this is going to be negative, minus 1.706. For this one, it's going to be minus 0.972. Right? Once we are done with that, we are going to do our carryover moment here. Okay, this is the carryover moment stage. We're going to say half of this is going to be added to that, which is 0.972 times 0.5 equals, which is going to give me 0.486. For this one is going to be minus 0.486. okay, for this one is 1.706 times 0.25 times 0.5, which is going to be minus 0.853, 0.853, like this. Okay, these figures are very low. Let me do a moment distribution and I'll end it there. Okay, for a moment distribution here, we're only multiplying this with the factor, which is going to be 0.853 times 0.363, which is going to give me 0.309. Let me just say 10 here. Okay, then the other one is 637, enter. It's going to give me 0.543. so this one is going to be negative, minus 0.543. This one is going to be minus 0.310. okay, now we are done. We are going to do our additions here, then we will draw the bending moment diagram. Okay, for this one we're going to add these ones, which is going to be 4,7916 plus 1,526 plus 0,486 equals, this will give me a moment of 6,8036. okay, for this one, let me add this one. This one is similar to this one. You'll find out soon enough. Okay, let's start. We will start adding from here going downwards. Okay, so we've got 9.5832 plus this other one 3,0522 plus 0,972 plus 0,31 equals, it's going to give me 13,9174. okay, this one is going to be in the negative. It should be similar to this one. Let's just check. Okay, here we have got minus 26.4 plus 16.81816 8 minus 8 comma 40 8 4 plus 5 comma 3 5 6 minus 2 comma 6 2 comma 6 7 8 plus 1 comma 7 0 6 minus 0 comma 8 5 3 plus 0 comma 5 4. Okay, it's now similar. It's minus 13 comma 9 174. Okay, this is going to be the same as the next one, which is going this one. Since this one is going to be positive, so 13 comma 9 174. This is going to be minus 13 comma 9 174. This is going to be similar to this one, which is 6 comma 8 0. This one is going to be, I'm not sure about that, but I will just write 3 6 like this. Okay, so these are the numbers that we've got. Now what we are going to do, we are going to draw a bending moment diagram. Okay, now we are going to draw the bending moment diagram. It's going to be like this. Okay, this is my A, my B, my C, my D. Okay, here the moment is going to be like this. You need to go to this direction like this. And for this one, it's going to be like this, like this, like this. And for this one, it's going to be like this. Okay, so these values here that we have, the values that we have here, this one is going to be here, which is 6.8. Let's just say 6.8036. Then this one is going to be 6.8036. Right, for this one we're going to use this one, which is 13 comma 9.9174. This is going to be 13 comma 9174. This is going to be 13 comma 9174. 13 comma 9174. Okay, these are the moments. Right, for this moment here, if you still remember what you do, you add lines like this. Then this is going to be 13 comma 9174. Okay, this is going to be the same value. Right, if we find the midspan moment here, it's going to be omega L squared divided by 8, which is going to be, remember, let me check what was the load that we used was 8. So around 8.8 times 6 squared divided by 8, which is going to be, let me just calculate that one. It's going to be 8.8 times 6 squared divided by 8 equals, it's going to be 39.6 kilonewton meters. Okay, this value is going to be here like this. It's going to be here somewhere here, which is 39 point something. So the one that we want, which is going to be the midspan moment, is going to be the difference between the two. Since these are constant, we are going to say 39.6 minus this one, which is 13.9174 equals, okay, it means that this moment is going to be 25.68, which means that the moment here is going to be 25.68 kilonewton meters. Okay, now these are the values that we are going to use for our calculations of the beam. The beam is going to carry what is called an end moment here, and it's going to carry an end moment here. So if we are designing for the top steel, by what I mean by top steel, if we have a beam like this one, there's steel that we add here, there's steel that we add here, there's steel that we add here. These three are for moments, right? The one that we add here and here will be determined by this moment here. The one that we add here will be determined by this moment here, and the one that we add here will be determined by this moment. Then when you are designing for the column, The column that we are the moment that we are going to use is this one, since it is the greatest moment that we are going to. I am sure it's that easy. Okay, so I'm going to let me just use an Excel sheet for this one, so that we end it in record time. Okay, thank you. Okay, now this is the drawing that the same calculation that I've done using a software called Study Pro. I've done my calculation using this. I've actually entered the same details, the same loading. I got the exact same answer. Okay, so these are the forces that you come up with. Now, when you have those forces, what you need to do is to calculate what is called what is my reinforcement. I'm going to do a rectangular beam. Okay, with a rectangular beam, this is where you add the moment. So the most significant moment is going to be this moment here, which is minus 25.8. Okay, the minus just means it has to do with the direction. Okay, so it's going to be 25.8. Okay, so the span is going to be 6 meters. The beam is going to have a depth of 400 millimeters. It's going to have a breadth of 230. Top steel, I'm going to use Y12. Compression, I'm going to use failed on maximum spacing. Okay, it's a matter of spacing, so I'm going to use 16. Okay, now it's correct. I'm going to use grade 25 of concrete. I'm going to use a concrete cover of, let's say, 35. Then this I'm going to use 35. This one I'm going to use 35. You'll find out that 2y16 is going to provide an area of steel of 4002 millimeter square millimeter. The minimum, the actual that we wanted was 174 square millimeters of steel. Okay, so for the moments, I think we are done. This is how you do your calculation. I decided to use this thing. It's bs8110 of 1997. Okay, for the shear, you go to the shear. For the shear, we need to come up with the shear value. Shear value, you can find it like this. It's 8.8 times the span, which is 3, which is half. It's going to give me 26.4. Okay, so the shear force that we are going to have, the grade of concrete is 25. Okay, we are going to have 2 links. Bottom steel is Y16. Links, they are Y10, and I want to use Y10. 2 legs, side covers, I think we are correct. Now this is going to be 26.4 kilonewtons. Okay, so you find out that it is correct. So this is how you calculate. This is going to be a beam, as you can see. Now for here, it's going to be it's not simply sampled. It could be continuous. You can say continuous like this. Then you copy this one. You say Control C. Then you paste it into this box here. Control V. Okay. Now we are correct. It's going to calculate the deflection in the right way. So this is the answer that we get. Thank you for your time. Subscribe, like, and share. Thank you.